This year in ME 2110, our competition revolved around completing 5 different tasks with a theme of a mission to Mars. The 5 tasks were to remove radioactive material from your zone, retrieve the rock samples, deposit spacecraft into safe zones, drop a flag in the center, and collect the astronauts and rovers off the mountain. This is our house of quality that we use to evaluate what design goals best corresponded to customer needs. The most important engineering requirements were the length, width, height, functionality after repeated cycles, time to carry out functions, and cost of materials. The length, width, and height were constrained to fit in a box that was 12 by 24 by 18 inches. The functionality after repeated cycles was important because the machine needed to perform all its tasks throughout the competition. This also needed to be done in a timely manner, as we were competing with other groups for the astronauts in the center. Finally, the overall budget was $100. The most important customer requirements were fits within size constraints, able to be used multiple times, deposit spacecraft, retrieve astronauts and rovers, and deposit the flag. This was due to the fact that, in order to compete, it had to be able to run multiple times while fitting in the size constraints. Also, these tasks were worth the most points, with the flag being weighted the highest. This was our specification sheet. The 3 most important categories were run on startup, the size constraint, as well as being able to run for at least 50 cycles. This was because if our machine failed to run on startup or to box, we would be disqualified in the competition. Further, if our machine wasn't able to run repeatedly, we wouldn't be able to compete in the competition and win. We selected our Mars rover concept for our final design. This design was able to perform 4 of the tasks: deposit spacecraft, deposit flag, collect rocks, and collect the astronauts. The first subsystem of our machine was a 2-gear drive that drove the cart forward. Using 2 water jet aluminum gears, we used the small gear to drive the big gear, which was connected to the axle that drove 4 lawnmower wheels, allowing our cart to go forward. We chose front wheel drive because when our cart was returning back up the ramp, the drive being in the back made it easier for it to get up the slope. The next subsystem of our design was a tube that held the spacecraft. We used 2 long arm switches that, when both pressed down, caused the solenoid to retract and release the spacecraft. Our next subsystem accomplished 2 tasks in one. It was a lever arm connected to the motor, which rotated around to drop the flag as well as collect incoming astronauts and rovers. Our final subsystem collected the rocks. It was a gate mounted on a solenoid that, when the solenoid was retracted, dropped and allowed us to drag the rocks back into the home zone. We also considered a few alternative designs, the first of which we called Hot Wheels. This design featured 2 motors driving the wheels, a pneumatic piston to push the spacecraft in, a rotating arm to block astronauts and deposit the flag, and a solenoid drop gate. The pros of this design were the reliable and safe deposit of the spacecraft, as well as the solenoid gate. The cons include using 2 motors to drive the wheels, making it difficult to drive straight, as well as an unreliable mechanism to catch the astronauts and rovers, and no ability to hit the tennis balls. Our next design was called the Extendo, unfortunately. The pros of this design was due to the unique scissor arm design, which allowed placement of the flag and collecting the astronauts and rovers quickly and easily. The cons were that the motors mounted below the cart to drive the wheels led to issues in collecting the rocks, as they would interfere as the cart moved over the rocks. Third design was called the tractor. The pros of this design were that one mechanism was able to complete 4 different tasks. The arm featured a solenoid-powered rover depositor, as well as an arm to swing out to hit one side of the tennis balls, and also to collect the astronauts and rovers and place the flag. The con, however, was that this design also featured the 2-motor drive system, which made it difficult to drive in a straight line, as well as having a source of unreliability in the swivel arm that would struggle to be consistent. Our final design was called the Model T. The pros of this design included a good rock collecting gate, as well as a consistent way to deposit the spacecraft. The con, however, was that the lever arm which would place the flag and collect astronauts was powered by a mousetrap, which led to inconsistency, as mousetraps are unreliable and prone to breaking. After considering all our designs, we settled on the Mars rover for our final design, as it received a score slightly higher than that of the Hot Wheels design, 252 to 245. We also valued the reliability of the gear drive mechanism and flag placement mechanism. Further, we felt that the lawnmower wheels would be more reliable than the laser cut wheels featured in Hot Wheel and many of the other designs. We ended up getting the 57th seed in the qualifying round, out of 61. This was the result of 3 scores of negative 48 points and 1 disqualification. However, we were able to turn it around in time for the competition, as we ended up advancing to the 3rd round after placing 1st and 2nd in the 1st and 2nd rounds respectively. We were able to win the 1st round due to a tiebreaker, as we had collected a rock while the other group had gotten an extra rover, with the rock being used to break the tie. Overall, we were satisfied with our performance in the competition with our revolutionary design, but we had been hoping to advance further into the competition.